Okay, so this is week 3 of your semester, right? And in the first 2 weeks, you have seen some basic introduction to what is deep learning, what are some basic concepts like activation functions, softmax, one-hot encoding, right? And then in the previous week, we started with neural networks, right? So actually, this course is all about neural networks. You must have seen them in a course on machine learning, right? But some basic, you can say, building blocks, which are very much required for this course. So I thought we should not skip them, and we should make sure that all of the students are at the same level before we dive deep into neural networks, right? So we started with perceptron in the last week, right? Perceptron is a single neuron with a step activation function which can solve a linearly separable problem, if you remember, right? And in the last 10 minutes, I think we started this discussion on logistic regression. And I had asked you what is the difference between classification and regression. So it was good that almost all of you knew it, that in classification, the variable we are trying to predict is discrete, whereas in regression, the variable we are trying to predict is continuous, right? And I had given you an example that if we are trying to predict your grade from some features, then this is a classification problem. But if I'm trying to predict your GPA, then it is a real number between 0 and 4. So it is an example of a regression problem. So, but when we talk of logistic regression, so the title could be misleading because it says regression, but actually it is a classification problem. And more specifically, logistic regression refers to a two-class classification problem, right? So we had seen some initial slide, but so let me quickly go through them. That this is the example I had given you, that it's a binary classification problem. For example, you are given with an image and you have to tell whether this image contains an object or not, right? For example, whether this image contains a cat or not. So the output would be either 1 or 0. So since logistic regression is a linear classifier, so if you have two features, like if you have, say, two features, x1 and x2, so it will separate the two classes by a straight line, right? But if, on the other hand, you are in a three-dimensional space, right? So I told you that the linear thing in a three-dimensional space is called a plane, right? So you'll have a plane because plane is linear, which will try to separate the classes. And if you have more than 3 dimensions, then your decision surface would be a hyperplane. But in any case, it would stay linear, right? So then I think this is what you have already seen, that we have some feature in an n-dimensional space, right? R means real number, n is the dimension. You have weights because for every feature x, you have a respective weight, and then you have a bias, which is a single number. So what you do is you take the dot product, right? For example, if you have, say, 3 inputs, so you will have a vector of 3 weights like this, and you will have 3 features like x1, x2, x3. So you multiply corresponding values together. That is why we can represent it as a dot product, right? Or you can write it as W transpose X, where W is the vector of weights and X is the vector of input, right? And then you can add the bias to it. You apply the activation function. And as we discussed, that rather than a step activation function, which is a harsh function, which gives you either 0 or 1, we prefer, you can say, a smoother version, which is the sigmoid, right? Sigmoid gives you any output between 0 and 1, so you can interpret it as a probability, right? So this is a visual illustration that if you have n features, you have n weights, you multiply them together and you apply the sigmoid. So I think these are the examples we were doing last time, okay? And they will actually give you an idea how the perceptron is trying to learn the decision boundary, okay? So I'll give you a link where all of this code is available, but the focus is not to understand the code, but to see what is being done here. So here we have two classes randomly generated 1000 point, right? And what we do is we try to implement logistic regression, right? So for logistic regression, you have one single neuron, okay, and you have two inputs, right? So as I told you, I'll not be explaining you the syntax, but I'll just give a quick walkthrough of the code. For the implementation, you will have complete practicals available to you. So when you say unit 1, it means I have one neuron, right? Input shape 2, it means it has two inputs, x1 and x2. Why two inputs? Because we are in a two-dimensional space, okay? You have one feature on this axis and the other feature on this axis. And then, as we said, this is the activation function sigmoid because we want an output between 0 and 1, okay? If it's a two-class problem, then you use a loss which is called binary cross entropy, right? So I'm sure you must be knowing it from machine learning. And then this is the function which actually implements the learning, okay? Maybe the gradient descent algorithm. So this is when once you write model.fit, so at the back end you have the complete learning which you had seen in the previous lecture, and the weights are learned. So initially these weights are some random values, W1, W2. So you based on the data that it sees, it will try to learn the weights and optimize the decision boundary, right? So these are the explanation which you can go through. And eventually, if you see that on this axis, you have the epochs, right? Once you are training it. And the blue one is the accuracy, which is almost, it's a simple problem. So it is, even in the beginning, it is very high and almost 100%. And this is the loss, okay? So if you see this, you see, this is the region in which your output is 1. Means the network is very sure it is class 1. Network is very sure it is class 0. This is some region in which you have, you can see the color coding. For example, here maybe the probability is 0.75, and maybe here the probability is like 0.25. So it is close to 0 and this is close to 1, right? So the reason is that since this region is at the boundary of two classes, so that's why the classifier is not very sure. The confidence of the classifier is not very high. On the other hand, if you talk of these points, which are very away from the decision boundary, so you see the classifier is very, very confident in assigning 1 to the blue dots and assigning 0 to the red dots, right? As you move close to the decision boundary, the classifier gets a bit shaky, which is very much natural. Okay, so I think this was the last slide we had seen in the previous week. So now let's complicate things a bit more for the classifier. Okay, now you have some data. You can generate this data by this function make moons. Okay, so now this data, you cannot separate this data with a straight line. Okay, but we know that logistic regression, the best it can do is draw a straight line. So let's see if we give such a data to Perceptron, how does it behave, right? So again, we have exactly the same piece of code, but here you see with epochs, its accuracy is not going beyond a certain threshold, right? Because no matter how good it does, it cannot generate anything beyond a straight line, right? So there's an empirical limit that how much accuracy it can achieve. And if you see it visually, you will know why. So you see, this is how it has tried to divide these regions, right? So maybe what you see here, this is where it is zero 0.5, right? So you can assume that anything on this side, you can classify it as red, anything on this side, you can classify it as blue. But now you see there's a very small region in which your classifier is very sure. So this is the region, these are the dots for which the classifier is very sure that either it's a class 1 or 0. But there are a lot of points like these and these, right, which are overlapping. So your classifier is confused, right? For example, in this region, it is saying that there's a probability of like 0.25, which is close to 0, that it belongs to red class. But in other words, it means all of these blue points which are here, they will be wrongly classified. Okay, so they will actually be classified incorrectly. Same is the case here, right? That these are the points where the classifier is giving maybe something close to 0.6 or 0.7. So we are tempted to assign them to the blue class, but then it means that all of these red dots, they will also be categorized as blue dots. So that is the reason, if you go back, that your accuracy is not going beyond a certain, maybe 82%, 83%, right? You can check the numbers. That always, no matter what, how good you do, there will be some points which will be wrongly classified. And then we make life even tougher for logistic regression, right? And we see, okay, what will happen in such a situation, because this is even trickier as compared to the previous case, right? So you see now that again, the accuracy is much lower as compared to the second case. And if you see the decision boundary or the decision region, it is something like this, right? So maybe there's a very small part, all of these, you see, for all of this region, your classifier is confused whether to classify it as a 0 or 1, right? Because this blue part is encircled by the red dot. So your classifier is by no way it can find a boundary which will separate these two classes, right? So this is a limitation of, you can say, logistic regression, but we are aware of this. The idea of showing you these examples was that we just get to know if such a data is fed to logistic regression or a linear classifier, how will it behave, right? So we'll try and solve the same problem using a multi-layer perceptron, which will allow us to do better than linear classification. But we'll do that after the prayer break, right? So maybe we take a break and then we rejoin, we see the same examples with a multi-layer perceptron. Okay. Okay, now we have seen three different case studies which we were trying to solve with the perceptron. Now we'll revisit the same problem with a multi-layer perceptron, or what you call, you can say, neural network with hidden layers, right? And please do remember that I told you in the one of the earlier lectures as well, that when the perceptron was first, you can say, came to scene in say 1958, the perceptron meant a step function, means plus one or and one or zero, or plus one minus one, right? So later on, this activation function was replaced by sigmoid, right? But the term perceptron, uh, due to historical reason, it persisted. Okay, so when you say MLP, so it means multi-layer perceptron, as I'll show you in the next slides, that it is a neural network which has multiple layers. But actually, you see, technically, they are not perceptron because they are not necessarily using the step function. They might be using sigmoid or ReLU or any other activation function, right? But since the term perceptron has continued for so many years, that's why you will see this terminology perceptron. So don't be confused that perceptron is supposed to use only a step function. Yes, it is true technically, but today if you are using the term multi-layer perceptron, you can have any activation function other than the step function as well. Okay, so perceptron was 1958. About a decade later, we had this multi-layer perceptron, and the origin was thanks to this problem of exclusive OR, right? I think we had seen this in the previous week, that a single perceptron cannot solve this problem, right? Because a perceptron can draw a straight line, and in order to solve this problem, you actually need two lines, okay? Because these are the two objects which belong to one class, and these are the two objects which belong to the other class, right? So I cannot draw one single line which can put the orange dots on one side and the black dots on another side, right? So it was in 1969 that using a multi-layer perceptron, this problem was solved, okay? And then actually that was the revival of neural networks. So formally today, if we define a multi-layer perceptron, it is simply a feed-forward network which has one or more hidden layers between input and output, right? Previously, if you remember, we just had this input layer and we had this output, right? There was no concept of something in between input and output, right? So if you put one or more hidden layers between input or output, that is in simplest words, a multi-layer perceptron, or what you call ANN in general terms, right? So again, another example, this time we have two hidden layers, okay? Now, what is going on in each layer? It is the same operation that you have inputs, and every input has a connection to the next neuron. Each connection has a weight, so you have the same thing, dot product. The vector is multiplied by the weights. So if you expand it, so basically the corresponding inputs are being multiplied by the corresponding weights. It means x1 is multiplied with w1 plus x2 multiplied with w2, and so on, right? And then you will add a Bayes term, and you will apply some activation function, which could be anything. Now, since we now have many connections, so it's a good idea to formally have some notation to represent the weights and the Bayes values, right? So it's fairly simple. Suppose I have three neurons in the input layer and four here, right? Since ANN implement a fully connected architecture, so it means every neuron in layer I minus one is connected to every other neuron in layer I. So if I have three neurons here and four here, so from simple arithmetic, you can tell that there are 12 connections, right? You can count them, there are 12 connections. So normally it means if there are 12 connections, I will have 12 weights, okay? So notation wise, we organize those weights in a matrix, right? And you see, you have three neurons here, four here, so we'll have a matrix of 3 cross 4, right? Which is actually 12 weights. And we call it W1, maybe matrix for layer 1. Similarly, here you have 4 neurons in this layer and 4 in the next layer. So it means your weight matrix for this layer would be 4 cross 4 because you have 16 connections. So you need 16 weights. And finally, you have 1 neuron here and 4 in the previous layer. So you will have 4 connection and 4 weight values, right? So these weights are actually the parameters which your system learns through training, right? We had done an example of a perceptron of, I think, AND gate, but in that case, you were learning only 2 weights. If you remember W1 and W2, I had shown you a complete numerical example. But of course, when you are dealing with relatively larger neural networks, you will have much more than only 2 weights, right? For example, in this case, the total number of weights is like 12 plus 16 plus 4 and plus Bayes values for every neuron, which I have not shown here. Okay, so now you see, why ANNs have been so popular, because they can learn any function, right? Means no matter how complex the decision boundary is, if you have smartly chosen an architecture and you have sufficient training data, a neural multi-layer perceptron can learn any decision boundary, and due to this feature, they are called universal function approximators, right? Means no matter how complex the decision boundary is, there will be some architecture with sufficient training data that would be able to learn that decision boundary. Okay, now let's solve the same problems, but this time we make a multi-layer perceptron. Okay, so what we are doing is that we have two inputs. Okay, so we have two inputs like x1 and x2. Then in the next layer, we put 4 neurons. Okay, so basically it means this is connected to all 4. Okay, similarly, x2 is also connected to all 4, right? So what I have drawn corresponding to that, I have this statement in Keras, okay, or TensorFlow. I have a fully connected layer, dense, 4 neurons. And since it is the first layer, I need to tell how many inputs are there. There are 2 inputs, okay? After that, I have 2 neurons. So I have written 2 here, so it means there are 2 in the next layer. And finally, I have 1 neuron. So this is the architecture. So you see there are 3 layers, and we have only 3 statements, one corresponding to each layer. So it's one-to-one correspondence, okay? And again, we are solving a 2-class problem, so the activation function is sigmoid. Now you see this architecture is much more complex as compared to a single perceptron. So now if we train it, this is the same data that we have seen previously. I'll show you on the next slide, okay? This is the training curve that the accuracy after certain epochs reaches 100%, and your loss is almost 0. And you see this is the decision boundary, which was a difficult case. Okay, logistic regression was not able to solve it, but you see that the boundary, this is your decision boundary, which is nearly perfect, right? You cannot ask for a better decision boundary than this. So it means, as I told you, that since they can learn any complex decision boundary, so here is an illustration. You can actually execute this code and visualize the decision boundary. Okay, I'll show you the link and towards the end of the discussion. Then we see what happens if we give it the second more challenging data set. So you see again, it is, I think, on training data, your classification is 100%, right? And the decision boundary is this one, okay? So there is not a single example which is misclassified. Why? Because our model was a multi-layer perceptron. Had we previously, we have been using simply one neuron, one perceptron, so that's why we were not able to, you can say, get such decision boundaries. Okay, so in this example, we are solving a 2-class problem. Okay, but you see, we can easily have a situation where we may have more than 2 classes. Okay, maybe 3 classes or 4 classes. So the generalization of logistic regression is called softmax regression, right? It's the same thing as logistic regression, but in logistic regression, the number of classes is 2. But when we say softmax regression, the number of classes can be anything, right? 3, 4, 5, whatever it is. So now this is an example. Maybe you are not able to see this part. It is in yellow, right? So if on your screen you can't see, these are yellow dots. Okay. So in this example, we have 3 classes: blue, red, and yellow. And again, the data cannot be separated into by straight lines. Okay. So it means we can already guess that when we apply softmax regression, although we are solving a multi-class problem, but the model still is linear. Okay, so it is just a generalization of logistic regression. The power of the model does not change. It stays linear. So you can already guess that maybe with this we will not be able to solve this problem, but we hope that this one would give us something much better. Okay. And the important thing is, which if it were a live class, I would have asked you that, you see, when we are solving a 2-class problem, okay, maybe with perceptron or multi-layer perceptron, whatever it is. Suppose we are solving a 2-class problem. There are 2 inputs. These are the hidden layers, okay, and these are my inputs, and this is my output, right? So although we are solving a 2-class problem, but at the output we only have 1 neuron. Okay, there is only one single neuron at the output. On the other hand, when I am solving a 3-class problem or 4-class problem, I will always ask you that the number of neurons in the last layer is equal to the number of classes. For example, if it's a 3-class problem, then the last layer will have 3 neurons. If it's a 10-class problem, if I'm trying to recognize digits from 0 to 9, then the last layer will have 10 neurons, so every neuron for one class, right? But here, when we were solving a 2-class problem, we did not have 2 neurons. We only had 1 neuron. And the reason for that is that you see, we are applying sigmoid activation function, which is giving you an output between 0 and 1, which is interpreted as a probability. So if I give this neuron an image, okay, and maybe I ask whether this image contains a face or not, okay. So you see, suppose its output is 0.8, that neuron is saying, sorry, the system is saying that there's 80% chance that this image contains a face. But since we know that the sum of probabilities is 1, so the probability of not having a face, I can simply subtract it from 1 and I can get it. Okay. So if we are solving a logistic regression problem, so you see why we are using only one neuron, because if I know that the probability of cat is 0.6, I know that the probability of not seeing the cat is zero point 0.4. Okay, I can simply subtract it. But this is not true if I have 3 classes or 4 classes, right? For example, if I have 3 classes, then of course I need a separate probability for each of these, something like this. So this is why when we are solving a 2-class problem, your last layer will have only one neuron, because you can find the probability of other class simply by subtracting from 1. And on the other hand, if you are trying to solve a multi-class problem, which is in which the number of classes is greater than 2, the number of neurons in the final layer will always be equal to the number of classes. Okay, so with that preamble, let's move ahead. Okay, so now you see, this is basically softmax regression. Means the same thing which you were doing in generalized in logistic regression. It means there are no hidden layers actually. Okay, so what is happening is that this is your output and your input is directly connected to it, right? So in input you have 2 variables and then you have 3 neurons in the output. So there is no hidden layer actually. This is your input layer, this is your output layer. Okay, that's why we are calling it softmax regression. Okay, another difference you must have seen that for 2-class problem we were using sigmoid as activation function. When it's a multi-class problem, we use softmax, right? And we discussed very much in detail in the week 1 that what is softmax, how do you compute it? It will convert your raw scores into probabilities. Okay, so already you can witness few differences, which are pretty standard. Whenever you are solving a classification problem with multiple classes, the activation function would be softmax, right? Another difference is that for 2-class problem, we use binary cross entropy as the loss function, and for multi-class, we have categorical cross entropy. Okay. One new statement which was not there previously. This statement, what is it doing? You don't need to memorize these. Okay, I'm just giving you a walkthrough. This statement is converting your labels into one hot representation. If you remember, we have 3 classes. Okay, so one hot representation, for example, if I have 3 classes like apple, orange, and peach. Okay, so if I have an apple, how do I represent that apple? I put 1 here and these 2 are 0. Okay, if I see maybe an orange, okay, then orange is represented by this. Okay, so you don't need to manually do this. Okay, we discuss it again in the first week. There's a function to categorical and you can just call it, it will automatically do this for you. Okay, so now with that, if we see what these are the details, okay, you can go through them about the code. So now you see this is how your curve is evolving, and this is what we need to discuss. So as I told you that softmax regression is also a linear classifier. Okay, so that's why whatever it will generate, they will always be straight line, right? So this is the decision boundary it could find, and you see it has made its best effort. So you see these points are correctly classified, the red ones, and then these points and these points. But of course, since there is a lot of overlap between data, and we can easily see that this problem cannot be solved with a linear classifier, but still the classifier has tried its best to actually assign maximum training data to the correct class. Now we do the same thing with relatively complex architecture, right? So we have one hidden layer where you have 64 neurons, right? It's then you have 32, 16, and eventually you have 3 neurons and the softmax activation function, right? So now if you see what decision boundaries do we get? So you see again, this is almost not almost, it is actually a perfect classification of this training data, right? There's not a, I can't find a single point which is misclassified. Why? Because we are using a multi-layer perceptron which can learn any complex decision boundary. Okay, so you can see it here. Okay, now if you want to generate this data, okay, and you want to visualize these decision boundaries, which is a good idea, one thing you can do is you can simply go to this link and download this course code. You can run it. Okay, so it will have explanation as well as you can generate any data. and it will actually show you the decision boundaries as well, right? So you can actually change data, play with it. You can change the number of layers, you can change the number of neurons, and you can see how the decision boundary is evolved. Okay, if you say no, that is too much of work, I don't want to do that, but I still I'm curious that how decision boundary is changed if I change the number of neurons or change the number of layers. If you don't want to execute the code, then there's a shortcut. Okay, and what is that shortcut? You can simply go to some web-based tool, for example this one. Okay, and you can play with them to convince yourself how things are working. Okay, so let me just do one example for you, and the rest you can do on your own. Okay, so let me just go to the browser, and we'll try we'll try execute it. Okay, okay, so maybe this is your browser, but let me go to. Okay, so now you can see the browser where you can select what data you want. I have selected the same data, so rather similar data which we had in our discussion. And now we can actually change what we want. Okay, so let me first have a situation where I have zero hidden layer. I don't have any hidden layer. Okay, and we use the sigmoid activation function. Okay, so let's try and do that. We are running it. Okay, so this is what you see here. This is actually training, right? But you see nothing much is changing because without any hidden layer, it cannot actually learn the decision boundary. So now I'll stop it and let me add one hidden layer. Okay, maybe you see you can change the number of neurons. So I have added one hidden layer with 3 neurons. Okay, and now let's see what it does. Okay, you see the loss is decreasing, and eventually it has converged, right? You see this blue part is one class and this is the other class. Okay, so now this is the decision boundary your network has formed. Okay, another important thing you must have learned that you see sigmoid is non-linear activation function, right? What will happen if I keep hidden layer, but my activation function is actually linear? Linear means that you don't have any non-linearity, right? Whatever comes, you simply add them and you pass it as it is. Okay, so what happens if I don't apply sigmoid activation function? So I do have a hidden layer. Okay, so you see now again it is not being able to converge, and the reason is that I'm using a linear activation function. The decision boundary is non-linear, so although I do have a hidden layer, but still it is not helping me out. Okay, so that's why you see the activation function is also important, that if the activation function is linear, the hidden layers would not be able to learn a non-linear decision boundary. So you see, so again, you can play with it. You can change the number of neurons, you can change the number of hidden layers. Okay, and you can also change the data, that how it works, and you can convince yourself. Okay, the better way is that you should run the code, but if you don't want to do that, at the least you should do this. Okay, so okay, so with all the preamble of perceptron and MLP, now we are in a position to see a real world example. Not truly a real world, but you can call it like the hello world of ANN, right? Which is basically, I think, the first program that you will write whenever you are designing a neural network, whether it's a MLP or whether it's a CNN, right? So the problem is actually handwritten digit recognition. So I'm sure you must be familiar with this. Maybe in a course on machine learning, you implemented it. So the idea is that you have handwritten images of digits, right? And you have to make a system which can tell you what image is it. So in other words, you will have you can say a scanned picture or a camera based image of a digit which has been written. It can be on a check, it can be on a notebook or anywhere, right? And you see, as a human, we can do this task almost effortlessly. Means we just see a digit, and even if it is distorted or not completely visible, we are still able to recognize it, right? But for a computer, it's a pretty challenging task. And why is it so? Because for a computer, when we are making a system, we'll give a matrix of numbers as an input, right? And since we are discussing neural networks, So a neural network has a fixed number of neurons at the input. So that's why we have to resize all images to a fixed size. Okay, so for this particular example, we have taken the size to be 28 cross 28, right? Means in this matrix, there are 28 rows and 28 columns. So in total, there are 784 values. If you multiply these two numbers together, you get 784. So we want a system in which we give this matrix as an input, and this system should give us the label that, for example, for this image, the output should be that this is digit 3, right? And we'll be using a neural network for this problem. So now let's go into some more details that what are actually these numbers. So actually, since in this example, we don't have any colored images, right? So we only have grayscale, or what you call, we should not call them black and white, right? Because there are shades of gray. So the correct term is maybe intensity image or a gray image, right? Just like a black and white TV that we used to have in 60s and 70s. So basically, every you can say matrix in the matrix you have 784 values, and every value is between 0 and 1, right? If it's close to 1, right, you will see something which is like white. If it is close to 0, you will see something which is like black. Okay, and of course if you have something like 0 0.5, 0 0.6, as you see here, it will be like gray, right? But there are very few portions in this image which are gray. Mostly the background is black, so you have values which are close to 0, and the foreground or the digit is white, which will be close to 1. Okay, so you see, for human, you can tell it's a digit 9, but for a computer, it just sees a bunch of numbers. There are 784 numbers, and it has to recognize the pattern, that when the pattern is like this, I have to output digit 9 and so on. Okay, so we'll design a neural network, right? So as I told you that since the neural network is one dimensional and this image is two dimensional, right? So there are 28 rows and 28 columns. So first we need to flatten it. Flatten means that suppose if I have a matrix like this, 1, 2, 3, 4, 5, 6, I need to convert it into a vector. So I can do it like 1, 2, 3, 4, 5, 6. So now you see it is one dimensional. So we do the same thing here. We have first row, second row, third row, we put them together. So we get, you can say, a vector of 784 values. Okay. So the input is fairly simple. The number of neurons in the input layer is same as the number of inputs, which in our example is 784. Now let's talk about output. So I told you a little earlier that the number of neurons in your output layer is always equal to number of classes. Since we are solving a digit recognition problem, so we have classes from 0 to 9, means there should be 10 neurons. So you see 10 neurons in the output layer, right? And then you can choose, okay, how many hidden layers I would have, maybe 2 hidden layers or 3 hidden layers, and then maybe how many neurons I will have. So in this example, maybe we are using 16 neurons in each of the hidden layer, right? So whenever we are discussing neural network or other similar topics, so there's a very typical query that how do you choose number of hidden layers? How do you choose how many neurons are in each layer? So you see, these are something which are called hyperparameters. Okay, so there's a difference between hyperparameter and parameter. Parameter is something that you learn. For example, weights are parameters, and hyperparameter is something that you fix before launching the learning algorithm, right? So since you have to decide before starting training that how many layers you need, how many neurons you need, so that's why we call them hyperparameters. And there's no rule, or you can say there's no criteria or fixed criteria that how do you choose these. It depends on the complexity of your problem. It depends on many other factors, right? So the best way is through hit and trial. By doing some experiments empirically, you come up with some good values, right? But with some experience, you can also guess, right? By looking at the complexity of data. Once you have sufficient experience playing with neural networks, you can actually guess, okay, what should be the right number. Maybe that guess is not correct, but you can always experiment, and then you can see whether you need to increase or decrease, right? So with some implementation, you will get an idea how to choose these numbers, right? Otherwise, there is no, you can say, rule of thumb that you should follow this rule in order to choose these numbers. Okay, now there's a slight, you can say, ambiguity about what these layers are actually learning. So you see, we are very clear what is input doing. We are very clear what is output doing, right? But this hidden part is somewhat non-intuitive, right? That we cannot tell that what feature these layers are learning in order to tell that the image on the left side is actually digit 9, right? So the best we can say is, as I told you, there's no intuitive explanation of what they are learning, but what we can say is that, for example, if I supply a digit 9, so of course some of these values will be high, okay, maybe these are high, and some values would be low. So it means whenever there is a 9, it is likely that even if there are variations, but there are there is a certain pattern, there is a certain set of neurons which would be active. By active I mean they have a high value, they have a value close to 1, right? So we can say that we have a specific pattern in one layer, and it will cause a specific pattern of activation in the next layer. For example, when I feed 9, maybe, and the weights have been learned, so when I multiply these inputs by the weight, I get maybe a pattern like this. And then when these values get multiplied by these weights, maybe I get a pattern like this. And for this pattern in this layer, I get a high value on the last layer for this last neuron. Okay. So in other words, what I'm trying to say is that you cannot tell what features actually these layers are learning. You can just say that for whenever the neurons see a picture like this, there will be a certain pattern of activation in one layer, which will subsequently cause another pattern in the next layer. And eventually at the last layer, we expect that if it's a digit 9, so you have a high value here, which is close to 1, and rest of all, they are actually close to 0. But when we move on to convolutional neural networks, then this will change, right? There we will have some intuitive explanation of actually what the network might be learning. But for a conventional ANN, we cannot tell what features actually it is looking for. Okay, another very important thing is that you should be given a neural network. You should be able to compute how many parameters are there. Okay, parameters means what you have to learn, the weights and the biases. Okay, so it's fairly simple. If you remember, we did some calculation that you have 784 neurons in this layer, and maybe in this layer you have 16. Okay, so the total number of connections are 784 into 16. Okay, and then if you move to this part, you have 16 here and 16 here. So it means there are total 16 into 16 connections. Then if you move to this part, you have 16 in the previous layer and 10 in the final layer. So you will have 16 into 10. So you add them together. These are the total number of weights for the connections. But for every neuron, other than the input layer, for every neuron in your hidden layers like this and the output layer, every neuron also has a bias, right? Which is, you can say, again, a parameter that you learn. So it means for the first hidden layer, I will have 16 values for the bias, then 16 values for the next hidden layer, and finally 10 values for this last layer. Okay, input, this is actually not a layer in the true sense, these are just input values, so you don't have any bias here. So if you add them together, you get a number like 13,000 something, which is the total number of parameters it has to learn. Okay, means that when you train it, you will initialize these 13,000 numbers with random values, and then by feeding it with some training data, as you have already seen, and after certain iterations, we expect that this network will be able to learn. It means it will be able to find the good values of weights for which the output is what we desire. Okay, now you see, let me just write some notation, and then maybe we can initiate the discussion session that what actually is going on. So what is going on is exactly what you already know. That let's take this example. Okay, so suppose I have 8 neurons in this first layer. This is the input layer. Okay, and this superscript you see when we write A0, it means we are talking about layer 0. Okay, and this is the first hidden layer. So what is actually happening is that all of these connections, right, they have some weight here. Okay, and of course let's call it 00, let's call it 01, and so on. Okay, so what is happening is A0 is being multiplied by this weight, A1 is being multiplied by this weight, and we already know, okay, that we can write it as a vector, as a dot product. Okay, so these are your weights, sorry, these are your inputs, A0, A1, AN, and if you have 10 inputs, you will have 10 weights value. So when you write it as a dot product, so this vector is multiplied by this, it means the first weight is multiplied with the first value, second weight gets multiplied with the second, you can say, input, and so on. Okay, I'll come back to bias later. Now, if you come to this neuron, what is actually happening? It will have some different weights, okay, because you have other connections. So these weights are different from the weights of this neuron. It again, if there are 8 neurons, you will have 8 weights, but they will have different values. But the input still is the same. It means now you have a different set of weights which are again multiplied by this. So what I can do it that for this second neuron, I can write those weights in the second row of this matrix. Okay. So what is happening that corresponding to this neuron, I have a weight vector here. But since those weights are being multiplied by the same input, so you see this will do the job. I don't need to repeat it again and again. Similarly, once you come to this third neuron, you will again have a different set of weights which you can write as the third row of this matrix. Okay, and again, once you multiply it with this vector, you get the corresponding output. So if we write it in a compact form, so you see it would be something like this, that you are multiplying these weights for the layer 1. We are talking only for the first layer, okay? And so this is your weight matrix, right? And what is the size of this matrix? You can compute, for example, if I have 1, 2, 3, 4, 5, I have 6 neurons here, and 1, 2, 3, these are 8. So you can easily tell that this matrix is like 8 cross 6. Okay? Or if you write it 6 cross 8, it's the same thing. It depends how you are doing the multiplication. Okay, but the important thing is there are a total of 48 weights. Okay? So now you see we also have a bias, but this bias is actually, we have how many bias? One for this, one for this, one for this, one for this. So you have 6 hidden neurons. So you will have 6 values of bias, and you can also put them in a vector like this. Okay, B6. So what happens is that once you multiply this matrix with this vector, you again get a vector of 6, which are these 6 values. You add 6 values of bias, and then you apply the activation function. So what you see here is actually can be represented in a compact notation like this, that this is the input. This is not a single value. This A is bold. It is representing this complete vector. Okay. This W is your weight matrix like this, and this B again is actually your bias vector. Okay, so for example, if I have 6 neuron, it means there are 6 values in this. And you perform this, you multiply the weight matrix with the vector, you again get a vector, you add bias, you apply activation function. This will give you 6 values, maybe like this 0.2, 0.3, 0.1, any values which are here. And then you repeat the same process for the subsequent layers, right? So nothing is new, it's the same process that we are doing, but the only difference is that now we have been repeatedly doing it. Previously in a perceptron we were doing it only once. Now we have multiple layers on which we are repeating this. Okay, so let me quickly conclude this, and we start the discussion session. That suppose now you have this architecture and you want to train it, so you already know it's supervised learning, so you will have data in the form of pairs, right? Means you will have a training example, maybe an image, and you will have the class label, right? So maybe this is X, this is Y, and you will have many such pairs. So what you do is that you initialize all the weights randomly. Okay, you feed it a training example, you multiply it with random weights, so you get something nonsense, right? It does not make any sense because these weights are random. Okay, but you all also know the ground truth. Okay, so we have already discussed that you know that if this is the input, this is the true output. Okay, this column, that this should be 1, rest everything should be 0, but you are getting this thing. Why? Because your network is not trained. So you already know what we do. We compute the cost, and for example, if you are using mean square error, so you can simply say this minus this whole square, this minus this whole square, and add them together. So this is basically the cost of this training example, and then you can repeat it for all the training example. And based on back propagation, which we'll see shortly, it will try to adjust the weights in such a way that, for example, if this is my image, I want a high value here and I'm getting 0.2. So your network knows that this value must be increased. Okay, the weights must be changed so that you get a higher value here. On the other hand, you are getting 0.8 for 1. Okay, but 1 should be 0. So it means this arrow is showing you that this is the value which needs to go down. Okay, and the bigger the arrow, the greater the reduction in value you desire. Okay, so you see, you can visually see that what we want, but mathematically you are telling the neuron, sorry, the network, that you have to adjust your weights in such a way that this value goes up and all the other values come down close to 0 for this particular training example. Okay. So if you want to implement something like that, it's fairly simple. Okay, so you see in the first layer you will have 784 input neurons, because this is the size of your image. Okay, in the output you have maybe 10 neurons, because there are 10 classes, and you can choose how many hidden layers you want and how many neurons you want. Okay, for example, in the example that I'll be showing you, I have chosen 512 each, but you can play with these numbers, maybe 256 or, or something else, right? So now if you want to convert this into a program, it's fairly simple, right? So you can load data, you can load labels, right? And actually, this is the key part, which is your network. Okay, we had 3 layers, so we have 3 lines. Okay, so we make a model. We add a layer which has 512 neurons, and for the first layer, you need to tell the size of input, which is 784. Okay, then another layer. Okay, and finally, this is your output layer. Why it has 10 neurons? Because 10 classes and your multi-class problem, so you are using the max function. Okay, so you can actually train this model. And this fit is actually that gradient descent. Okay, which or in this case, it is actually back propagation, which is based on gradient descent. And then you can actually test how good your model is. Okay, so I'll actually try and run this program for you, right? But that we'll do in a while. First, I think we can discuss, and if you have any queries, please tell me. Then I'll try run this program so that you see how training is being done. Okay, so now you have seen that model.fit. Now is the time we see what is going on at the back end, right? So the algorithm that we use to train a neural network, all that magic, that is called back propagation, right? And if you remember week 1, back propagation was proposed in the late 80s. Okay, I think 86 or some 88, I don't remember, late 80s. Okay, so that's why before that MLP, it was in 1969. Okay, but back propagation in 1980s, late 80s. So that's why in between we had that period which we called the winter of AI, because even if you could design multi-layer perceptron, there was no algorithm to train it, right? So that's why there was a period where people were not too much interested in neural networks. But after this back propagation in the late 80s, so the early 90s, that was the period when these ANNs actually saw their boost. Okay, so let's see how this works. So you see, when you feed some input to the network, you know what is going on. You simply multiply the input with the weight, whatever input you are feeding here. You have to multiply it with the weight, you add them together, and then you repeat this process. So actually, you are moving in this direction, which is called forward pass. And you already know how to do the forward pass. We have done it in the previous example. We multiply input by weight, we add by, apply the activation function, and so on, right? But you see, if the network is not trained, then we need to adjust these weights. So you have some weight here, you have some weight here, you have some weight here. Okay, and here you have target that, suppose if this is the image of 5, I want a 5 here. Okay, suppose you have these random values, so maybe instead of 5, you are getting some other value. For example, neuron is predicting that it is digit 2, which is wrong. So it means now you need to adjust this. Okay, but how do you adjust? You adjust in such a way that this number or whatever you are getting, you get as close as possible to 5. Okay, but the problem is that this value which you are predicting at the last layer, it is not only dependent on this weight, it is also dependent on this weight as well as this weight. So in other words, whatever you are trying to change at the last layer, it is affected by every single weight, right? Because if I change something here, this will change. If this will change, this will also change, and this will also change. So in other words, your error is dependent on some variables which are in this layer, the previous layer, and the previous layer, and so on. And now you can already guess that here we are interested in finding how error is changing with respect to my weights. And some of the weights will be here, but some of the weights are in some initial layers. So it means that in some time we are going to see that chain rule. Okay, so if you can link this, you should be able to guess that chain rule is coming up very soon. Okay, so this is the example that we'll be doing. Okay, but instead of doing it on the slides, I think it's a good idea that we do it on a board for once, because this is very, very important that you understand it once. And once you have done, you can blindly call the model.fit function. Okay, so let me just try to draw a clean version of this, that it is pleasing to your eyes and you don't lose the focus. Okay, so maybe this is our neuron and we have 2 inputs. Okay, okay. And within the neuron, there are 2 things that are being done. So let me split it into 2 parts. Okay, it is 1 unit, but just for discussion purposes, I have split it into 2 parts. Okay, so now what is going on here? We have x1, x2, which are two inputs. Okay, and we have w1, w2, which are two weights, but we don't know what are the values of these weights. We have given some random values, but we want them to be some good values. Now what is going on here? Okay, for this example, again, we are not considering bias, but so that we keep the discussion simple. Later on, we'll introduce bias as well. Okay, so you know what is going on here? We are doing this. We are computing z, which is actually summation wi xi. Okay, or in other words, maybe let me write it cleanly because there will be a lot of mess. So z is like w1 x1 plus w2 x2. Okay, so these z is basically the dot product, and then once you compute it, you don't output it first. You also apply some activation function, and suppose we are applying sigmoid on this. Okay, so z is this thing, and then this symbol is sigmoid, so you apply sigmoid to it, and whatever you get, you give it as an output. So this is your output. Okay, now you see what we need to do is we need to define an error, as I told you last time. Okay, that what is our error? So we say that the most common form of error is the mean square error, in which we say my error is the difference between the target value minus the output value. Okay, and we square it so that even if we have negative values, after taking the square, all the errors are positive values. Okay, so this is our error. We simply, for example, if I wanted the output as 3 and the output is 2, so I simply subtract them and I square them. Okay, and just to make our calculations are relatively simple, you see I'm multiplying it with a constant that is 1 by 2. Okay, it doesn't matter, because if I'm trying to find the minimum value, I multiply everything by 1 by 2, the minimum would still remain minimum. So it is perfectly legal to multiply it with a constant. Okay, now if you remember, how do we update weights? Okay, that is the key expression in gradient descent. So let me write it somewhere. So if you remember, it was something like wi is updated as a previous value of wi minus learning rate into derivative of error with respect to wi. Wi means if you have two weights, so I is first one, or and then I is two. If you have 13,000 weights, I will have 13,000 values, because you have to update every single weight in your network, right? So for simplicity, instead of writing wi, we can write it as a vector, right? W, which is bold, so it means we are talking about the vector of all the possible weights. Okay, so in other words, if I want to implement this, I know everything. Wi is initialized randomly, so I know this value. This eta is learning rate, it is a hyperparameter, I know this value. The only thing I don't know is this thing, right? And this is the thing which I need to compute. So in other words, I need to compute the derivative of error with respect to my weights. This is something I need to compute. Now, how do we do that? You see, if you, in the beginning of the lecture, someone asked about chain rule. So now it will become clear that you see, this is E, okay? And I have to compute the derivative of E with respect to W. But in this expression, we don't see W. We have target, which is given to us, and we have output. So the variable is actually output. But so it means I can compute derivative of E with respect to output. I cannot compute it directly with respect to W. But if you see, output is dependent on Z, and Z is dependent on W. So what we can do is, if we apply chain rule, I can split this expression something like, if I have to compute this, I will compute the derivative of error with respect to output, because that is the only variable I have within that expression. And output is actually sigmoid of Z. So output is dependent on Z. And what is Z? Z is dependent on W. So you see, now it makes sense that why we are using chain rule. So Z is dependent on W. So we have split the derivative of error into a product of three derivatives, because error was dependent on output. So I say derivative of error with respect to output. This output was dependent on Z, because we are taking sigmoid of Z. So we say take derivative of output with respect to Z. And this Z was dependent on W, right? When I say W, I means W1 or W2. So I take derivative of Z with respect to W. Now I can easily compute each of these three derivatives. Okay. So let's start with this first one. Okay, I will try to compute all on the same slide so that you can see the global information. Okay, let me just change the color so that it is visible. Okay, so now we are computing this one. Okay, it means we are computing derivative of this. So if I compute derivative of this with respect to out, you just see instead of out, this is x. So what will happen? This 2 will come here. Okay, and 2 and 2 will cancel. Now you can guess why I had written 1 by 2. So I will be left with target minus output. Okay, and this was 1 by 2, but the 2 that was here, it comes here. Okay, and then I take the derivative of whatever is inside the parentheses. So this is a constant, so it will become 0, and this is like derivative of minus x. So derivative of minus x is like minus 1. Okay, because we are taking derivative with respect to out. So this is like derivative of x minus x with respect to x is minus 1. So you get a minus 1 here. Okay, so it means that we have computed one term, that derivative of error with respect to output is minus target minus output. Okay, so this one part is done. Means the first term has been computed. Now here we are computing derivative of output with respect to z. So what was output? Output was actually sigmoid of z. So in other words, we have to take the derivative of this with respect to z. And if you remember, first half of week 2, we computed derivative of sigmoid. Okay, we computed it for today, so that today I don't have to explain you why we are saying like this. So the derivative of sigmoid, if sigmoid is say f, derivative is f into 1 minus f. Okay, we derived it in the second wave. If this is sigmoid, so the derivative is f into 1 minus f. Okay, instead of a f, we are using this symbol here. So if I compute the derivative of out with respect to z, I get sigmoid of z into 1 minus sigmoid of z. Or you see, sigmoid of z is actually the output, so I can also write it as out into 1 minus out. Why? Because output is actually sigmoid. Okay, and the derivative of sigmoid is this term. So whether you write sigmoid of z into 1 minus sigmoid of z, or you write out into 1 minus output, it's the same thing. Why it's the same thing? Because out is actually sigmoid of z. So now this term which you see here, this is derivative of this part. So we are done with these two. Now we need to compute the derivative of z with respect to w. It means now we are talking about this one. Now you see, as I told you, this w means it can be w1, w2, w3, and so on. Okay, so if I'm computing the derivative of this with respect to w1, what will happen? This term will become constant. Okay, and the derivative of this part with respect to w1 would be x1. If I'm computing derivative with respect to w2, this would become constant, and the derivative of this term with respect to w2 would be x2. Okay, so in other words, if I have many terms here, all those terms will end up 0 except only one term. In other words, if I'm computing derivative with respect to wi, the output I get is xi. Means if I'm computing derivative with respect to w1, output will be x1. Derivative with respect to w2, output would be x2. So in order to generalize it, I can represent it as xi. Now you see, I have to multiply all these three terms together, and then if I multiply them together, I will be able to find this. Okay, now I think I have no choice, but I just need to clear this and write it maybe in a neater way. So if I think I do remember what I computed. So it was something like, I think, a minus sign. Okay, I'll just rearrange it slightly, out into 1 minus out, and then we had target minus out, and then we have xi. So this is basically the derivative of error with respect to weight. And when I write w, you can actually write wi. Okay, this can be 1, 2, 3, and so on. So if you replace this in the weight update equation, that how actually weights are being updated. So our weight update equation was wi gets the value wi minus learning rate into derivative of error with respect to wi. So in place of this, I'll plug in this hole. So since this was minus, so this will become plus. So the final expression would be wi gets the value wi plus learning rate. Okay, and then you have out 1 minus out. This term is due to sigmoid. Okay, and then you have target minus out, and then you have xi. So now this is the key expression, which is, this is what is happening behind this model dot fit function in TensorFlow. This is what is happening. Okay, you have some random values, and then this is how it adjusts, and I'll numerically show you that how actually it takes you closer to the target. Okay, so let me first show you these cleaner version of this maybe on the slides, and then I'll open the house for some queries or discussion. Okay, so let's go back here. You can say neater version of the same thing. So we did this example. We have two inputs, x1 and x2, two weights. Okay, so within the neuron, we are taking the dot product, applying the activation function, and we are getting the output. Okay, so we say our error is target minus output. We take it square, which is common, so that we don't end up with negative values, and we multiply it with a constant because we want to cancel out this 2 when we take the derivative, right? So it is only for simplification purposes. Our objective is to find the derivative of error with respect to w, because this is the key term in the weight update equation. So you see, since the error is not directly dependent on w, so we need to use the chain rule, because error is dependent on out is dependent on z, and z is dependent on w. So using the chain rule, we can split the derivative into a product of 3 derivatives. So here we compute the derivative of error with respect to output. This was the term. When I compute derivative, this 2 comes here, it cancels out, and I get target minus output. And then I again take the derivative of this part, which is -1. That's why you see a minus. Derivative of sigmoid, we derived last time, it is f into 1 minus f. Instead of f, we are using this sigma symbol here. And since output is actually sigmoid, so you can either write this or you can also write this. Both are the same thing, right? Because actually your out is actually sigmoid of z. So that's why I have preferred this, so that you have output here and output here. It would be easier to correlate. Okay. And finally, this was your z. So when you take the derivative of this term with respect to wi, when I is 1, so I told you this term will be 0, and you only get x1. When I is 2, this term would be 0, and you only get x2. So if you generalize, if you have wi, you will end up with xi here. So if you multiply this and this together, you end up with this expression, which I derived a little while back on the board. And finally, your weight update equation will be something like this. This is a key expression, so I simply plugged in this value, and you get something like this. Since we had a minus here, so this minus cancels out, and that's why you see a plus sign here. Okay, so this is how you will update the weights only at the last layer of the network. I'm talking about the last layer because only on the last layer we have output. Okay, and we have target. For the intermediate layers, there is some other process, right? Not totally different, but we have to do something slightly different from this, because we cannot compute the error at the intermediate layer. For the final layer, we know what is the target, so we can simply take the difference, take the square, so we know what is the error. But for the intermediate layer, there is no intermediate target, right? So we need to have some other mechanism of finding the error, and that is what we call back propagation, right? But before we see that, I think this was some relatively heavy material, so let me take few queries if there are any. Yes, please, if you have any queries, please let me know. Okay, now let's extend our example to some realistic network, right? Because in the previous example, we just had a single neuron, right? But of course, you will not have a single neuron. Even if the network has one hidden layer, maybe at the last layer, you will have more than one neuron, right? So it means that every neuron will have a different output, and every neuron will have a different target, right? For example, if I'm solving some classification problem, I have 10 neurons, okay? So maybe the target for B is something else. Maybe target for B is 0, and the target for B, C is 1, okay? So maybe its target is like 0, its target is 1. And here I'm getting the output as 0.4, here I'm getting this, right? So it means you need to repeat that process at every node, okay? Because you can have multiple nodes at the last layer. So just to make our notation more clear, so you see, this is basically the terminology you can say, the expression that we computed. It looks a bit scary, but it's fairly simple. You see, instead of using this long, you can say expression, let's replace it by a variable error b. Means we call it what is the error at b. So it's very simple. Since you are using sigmoid, so the first term is output of b into 1 minus output b of b, and you already know this is the derivative of sigmoid. Okay, and then error is simply what was the desired output and what you are getting. So you see, if you see it conceptually, it is not as scary as it might appear once you first look at it. Okay, so just to keep our notation simple, we are replacing whole of this term by something which we are calling error. And why we are using this b? Because now I will have an error at b, and there is another neuron c. Okay, and maybe there is another neuron d, so I will need another variable which I'll be calling error at b. Okay, so now if you go back and see the expression for the weight update. Okay, so this is the part which I am calling e. Okay, sorry. So this is, let me just share again. Okay, yeah. So this is the part which I'm calling E. So it means the expression would be simplified that in place of this, I'll be replacing whole of this by E, and E with the subscript that whatever neuron I'm talking about. Okay. So now this whole E, okay, whatever you call it, is being multiplied by learning rate, and it is multiplied by xi. What is xi? Whatever input this neuron is getting, x1 or x2. Okay. Now if you go here, so now maybe if I try to write the weight update equation, so now my weight is WAB. So I will write something like the new value of this weight is the old value of this weight plus learning rate plus whole of this thing. Instead of whole of this, I will simply write error at B. And in the previous example, we were multiplying it with x1. Why x1? Because x1 was the input that was coming on this link. Now, what is the input that is coming on this link? There is no x1. Actually, the output of this neuron is the input to this neuron. Okay, so here what I will write here output of A. Okay, why? Because now the output of A is actually the input of this. Previously, we were doing like this. This was x1. So input to this neuron was x1. So I was multiplying that error with x1. Now here you don't see any x1. Here the input to this neuron is actually the output of this neuron. So that's why here I'll be writing output of A. Similarly, the same will be for this C. So let me show you these expressions. So you see, this is the expression which I was talking about. The new value of weight AB is old value plus learning rate, error of B, which is whole this term, multiplied by output of A, which is actually the input to this neuron, okay, which in the previous discussion was X1. And you can write a very similar expression to update the weight of the link AC. Okay, it's exactly the same thing. The only difference is that now you are multiplying it with error C, which makes sense. Okay. So you see, in this way, if you have 10 neurons in the last layer, you will have 10 such expressions, which is perfectly fine. Nothing much is changing, only this and this part would be different. Okay. So now we are in a position to update the weights of the last layer. Okay. But now still a challenge that remains is how do we update the weights of these layers? For example, there are also weights here, maybe some W here. The problem is that we need error. What is the error here? Okay, so for the last layer, we can compute the error because we know the target, but there is no target for the intermediate layer. So that is what is causing a problem. Okay, so here what we do is that whatever error we are getting here at the last layer, we will propagate it back to this layer. And that's why this algorithm is called back propagation. Okay, that since you don't have error at layers other than the last layer, so whatever error you are getting at the last layer, you will feed it in the reverse direction into the network so that the intermediate layers know how they have to update their weights. And this is the reason this algorithm is called back propagation. This is actually back propagation of error, nothing else. Okay, so now this is the key term, that if you want to compute what is the error at A, since A is using again sigmoid activation function, so with your eyes closed you can write this thing. Okay, this term is due to sigmoid, output of A into 1 minus output of A. Okay, this you should be able to write without any problem. Now, how do we compute error at A? Right, what we do is we had some error at B and some error at C. We'll back propagate is, and how do we do that? Error at B into this weight, okay, which makes sense because you are multiplying this error with this weight, so you are propagating here. But some error is also coming from here, so you have to add them together. Okay, so you have error from B weighted by this weight, and plus the error which is coming from here weighted by this weight. And suppose if you had a third neuron, you will have a third term here which will say error at D into WAD. Okay, so this is basically, and what is error B, error C? These are the same, you can say, which you have already computed. These are these things, okay, which we already computed. So you have pre-computed those values and you will simply back propagate them. So the key statement is this part, okay, where you are, this term you already know it is coming from the sigmoid. And since you don't have a direct target here, so what you do is you take the error at B, multiply it with this weight. So some part of error is coming from this path and some part of the error is coming from this path. You multiply them with the weight, you add them together, and we call it error at A. And now you can repeat the process from the previous layer. Then now you have error at A. So you can use the same weight update formula to actually update the weights which are on this layer. Okay. So you see now, suppose you had some weight here. So this is the weight update equation. Okay. And you want to compute the derivative of error with respect to weight. So since you already have this term error A, so you simply multiply it with x1, which was the input to this, and you would be able to update this weight. And what is error at A? Error of A is actually this term. Output of A, 1 minus output of A, and this is the error which is back propagated, and then you multiply it with x1. Okay, if you are wondering from where this is coming, okay, I have a complete derivation within the slides, but I'll not be covering it because I think it might be too heavy. Okay, but if someone is interested, the derivation is available, right? But you see, I have written here optional content. Optional content means that I will not be covering it. I will not be asking from you in any exam or an assignment that please derive it. I will never ask it, right? But if someone is interested and you want to actually see why we are multiplying error B with this weight and why error C with that weight, so the complete derivation is available in the slides, right? So if you want, you can see that eventually we end up with this, right? But there are a lot of derivatives, lot of chain rule. It might be a little too heavy to digest, especially once we are in an online mode, right? That's why I'm skipping this part. But if anyone wants to discuss offline other than the lecture, they can go through this content and tell me. I can explain them other than the class time, right? If someone is interested. Otherwise, you can skip this part. Okay, so this as well. Eventually, what I expect is that you should know this term. Okay, what I am skipping is if you are curious that from where this term is coming. Okay, but of course, this term you should be knowing. What I am skipping is how this term is derived. Okay, so the how part is optional, but the what part is not optional. It doesn't mean that you can skip the expression as well. Okay, so now with all that discussion, it won't be justified if we leave it as it is and we don't try to solve it by hand. Okay, so now is the time we try to at least do one iteration of back propagation on a network, right? With some expressions and then with some numbers. Okay, so you see it is a relatively complex neural network, right? Only one hidden layer, but once you are doing with hand, it is complex. Of course, for a computer, it's fairly simple. Okay, so you have two outputs. Okay, so it means I will have some error here, right, which I'm denoting by this symbol. So you will have error at alpha and error at beta. Okay, means you have some error here, some error here. And now with practice, you should be able to write blindly what would be that output of alpha into 1 minus of output of alpha, the same thing which you have been doing, and target at alpha minus output at alpha. Previously, we were calling them B and C. Here, the only difference is we are calling them alpha and beta, right? So that you see the same thing again and again with different symbols and it gets fixed into your mind. Similarly, once you are computing error at beta, it's output of beta 1 minus output of beta, again sigmoid, and target into this. Okay. Now, if you have to update this weight, okay, I'll show you on the slide, but you can guess what it would be. It should be the old value of this weight, something like this, plus learning rate into whatever error I have at alpha into what is the input to this neuron alpha. The input to this neuron is actually output of A. Okay, so it would be something like this. Okay, and similarly you can do if you want for this, you will have a similar expression, but this would be replaced by error at beta, right? So you see, you can write the expression for all the 6 links that you have or the 6 weights you have in the last layer. It's exactly the same thing. The only thing is that when you are talking about this, the input to beta, if you are talking about this link, is this output of B. That's why you see output of B here. Okay. So if you can write one expression you can write all 6 expression. Okay, so this is how you actually update the weights. A slightly tricky part is when we go to the first layer, okay, because we don't have you can say target there. So when we have to compute the error maybe at A, so what is error at A? Error at A is coming from, you can say, two different places. It is coming from this part, it is coming from this part, what you see in red. Okay, because these are the two which are connected. So whatever error you have at alpha and beta, you back propagate it to A. And how do we back propagate it? Error at alpha into this weight. Okay, similarly whatever error you have into this weight. So here you have, this is the same thing we were doing in previously when we were calling them B and C. Here only the notation is changed. Okay, so this is actually how you compute error at alpha, sorry, error at A. Then you do the same thing for B and C, right? I'll do one more example so that you understand. If I want to compute what is the error at C, okay, so error at C is coming from this link and this link. Okay, so it means you have to pick this weight and this weight, multiply it with error at alpha and beta, add them together, and then you have this term. And these are the same expressions which you have previously seen, so you can easily just plug in the values and do this. Okay, so now symbols can be a bit hard to understand, so numbers can be you can say relatively easier to follow. So now let's replace the symbol by some numbers. Let's feed some numbers. We have some weights. Okay, so suppose this is a network and we have randomly initialized some weights. Okay, and this is our first training example. Since this is the training example, this is supervised learning, so the target is 0.5, means this is what the value we want. Why? Right, because this is supervised learning, so you will always have a target. For every example you will have a target. And just to keep things simple, learning rate is 1. Practically, it will never be 1, but since we are doing it by hand, so it's a good idea we keep a value which can allow us easy multiplication. Okay. So now please see this carefully, right? Because this is something that I'll be asking from you, maybe in assignments or assessments. So it's a good idea to see how things are happening. Okay. So first we will perform a forward pass. Okay. So what is happening in the forward pass? Let's compute what is here. So this input is multiplied by 0.1, this into this. Okay, and what else is coming to see? This 0.9 multiplied by this 0.8. Okay, so you see 0.35 in this value multiplied by this, and zero point 0.9 multiplied by this. You add them together, you get this thing. But you also apply the activation function. So you take sigmoid. Okay, you can use a calculator or some internet tool to compute sigmoid. So sigmoid of 0.7 is 0.68. It means the value here is 0.68, which is actually the output of this neuron C. Similarly, you can do it for the bottom neuron. Okay, you can multiply the input by the weights. You get 0.68. You take sigmoid of 0.68, which is 0.63. Okay, and then here you have value which is 0.68. Here you have 0.66. You multiply this with zero point 0.3, you multiply this with 0.9, you add them together, you get 0.801. You take sigmoid, you get 0.69. Okay, so it means that your output is 0.69. But do you remember what was the target? The target was 0.5. So there is an error, which is okay. Why there is an error? Because the weights were random. The network is not trained yet. Okay, so now if we compute what is the error at the output, okay, I'll show you on the slide, but you should try and remember it should be out into 1 minus out into target minus out. So you see, what is the error at E? Out into 1 minus out into target minus out. Okay, since there is only one neuron, so whether you write E or not, it's okay, right? But just for clarity, I have written. So you have all these numbers. Out is 0.69, target is 0.5. Okay, so you can compute it, and once you compute it, it comes out to be 1 minus 0.69 into 0.69 and so on. Okay, so this is the error at neuron E. Now, if you have to update the weights, this is your expression. This is again the same expression that with which you are familiar. You simply have the old value of the weight. You multiply it with the learning rate. Okay, this is the old value of the weight CE. What is the old value of this weight? It is 0.3. Okay, and you simply multiply this 0.3 with with the learning rate, which is 1. You have just computed this term, which is here. And what is coming as input on this link? This is 0.68, okay, which is the output of this neuron C. So you multiply it with 0.68. So you have 0.3, which was the old value, learning rate, error, and the output of C. So you get a new value for this, which is 0.27. So you see now the weights are changing. Someone was asking how weights are changed. So now you can witness the weight being changed. Previous value was 0.3, the new value is 0.27. So some change is going on. Similarly, you can actually update this weight. Okay. So if I do that, it is the old value of the weight, which is zero point 0.9. Previously, it was 0 0.9 plus learning rate into error into whatever is coming as an input. So 0.66 is coming as an input. So you see 0.66 here. You multiply them, you add them together, you get 0.87. So you see both the weights have reduced. It means initial weights were a bit too high. 0.3 is reduced to 0.27 and 0.9 is reduced to 0.87. Now, for the hidden layer, what you need to do, you know that you have the error at this layer. So as I told you, since you don't know what is the error here, so you propagate this error backwards. And how do you propagate? Now you have one single link. This is the link. Okay. So you multiply the error which was here with this weight, and that would be the error at neuron C. So it's the same expression, right? But a little simplified, because in the previous example we had two neurons in the last layer. Now we have only one, so that's why this term is relatively simple. So if you want to compute error at C, it is output of C, 1 minus output of C, and then you multiply this error which you just computed on the previous slide with this weight, okay? But now the important thing is that you must notice that here we are using the new value of the weight, okay? This original value was 0.3, but now it has been updated. So you are not using the previous value, you have to use the new value or the updated value, which is 0.272. Okay, so here you have this error at C, and similarly you can compute error at D. Okay, you can do it on your own, and now you are in a position to update the base of the first layer. Okay, so if you want to update, it's exactly the same thing. You have the, for example, I do one example, maybe I do for this one. Okay, so you see the old value, learning rate, you have error at D, and what is coming as input on this link, this 0.9. Okay, so that's why you see a 0.9 here. So with that, this completes one iteration. Okay, this completes because we have updated weights once. Okay, so now if we see, these are the previous values of weight, and almost I think all the weights have dropped. Okay, means every weight which was initialized randomly, all the weights are going down. So it means that we need lower values of weight. But just to see if we are going in the right direction or not, what you can do is you can perform again a forward pass. Okay, so previously you see you, you were getting 0.69, okay, and your target was 0.5. If you now perform, so the difference was like 0.19. If you perform the forward pass with the new weights, now your difference would be this. Okay, it is not calculated, but you can do it for to convince yourself. So now you see you are getting closer to your target. It means you will keep on doing this, and eventually you will arrive close to your target, which is zero point 0.5 for this example. And if it is some other value for other examples, of course, but by changing the weights, you are actually going closer to your target. Okay, and one last slide, and then we discuss all of this. That you see, we have done this for one single training example, right? But in a data set, you will have multiple training example. So as I told you, what you do is that you will give multiple training example one by one. If it is stochastic gradient descent, if it's batch gradient descent, you will give all the data once, and then you will update the weights. Okay, we did it last week. You also had a question quiz today. And if it's a mini batch gradient descent, and suppose if your data set size is say 1000, so you say my batch size is 100, so it means you give 100 examples, you update the weights, then next 100 and update the weight, and so on, right? And once all the data set has exhausted, then you go back to your first training example, as we discussed in mini batch gradient descent in week 2 of the semester, right? So this was one complete worked example of forward pass and backward pass. Okay, and related to this, you will have your first assignment. Okay, I'll upload it maybe today. I'll give you ample time, more than 1 week, maybe 10 days to do that, right? So I'll be uploading the details on the course web page maybe tonight or tomorrow early morning. So please do that. And one of the parts of that assignment would be this back propagation. Okay, so that I think we can have some discussion on things that we have seen in the last half an hour.